Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Welcome to MIT's Faculty Forum Online. I'm Robbie Stewart, a graduate student in course 22, and I will serve as our moderator today. The broadcast today is sponsored in part by the MIT Federal Credit Union and MIT Professional Education. A reminder that after we hear from today's guest, we'll field questions for him, and so please use the Q&A feature on the Zoom toolbar to ask them, and we'll get to as many of the questions as time allows for. So joining us today is Professor Koroush Shirvan. He is the John Clark Hardwick Career Development Professor in the MIT Department of Nuclear Science and Engineering. Professor Shirvan earned his PhD from MIT in 2012. Today's talk is titled Harnessing the 100 Million-Fold Potential of Fission Energy, Fuel and Design Optimization. We hope you leave today with a better understanding and appreciation of some key innovations driving lower cost, safer, and more efficient nuclear energy plants. So with that, I'll let Professor Shirvan take it away.
All right, thanks, Robbie, for that introduction. It's my pleasure to give our alumni as well as the NS community this presentation. I'll first start discussing just nuclear energy in general, and then I'll go into some of the details of some of the work we're doing to try to address some of the grand challenges. All right, so first, for those of you who are not familiar with nuclear energy, nuclear energy makes up about 10% of world's electricity. And currently, coal is the #1 source in the world. In the US, it's no longer the #1 source, but in the world still continues to be the #1 source. And nuclear energy is actually, it exists in over 30 different countries. And there are 440 reactors distributed across those 30 countries. And you should know that 95% of these reactor technologies use water actually to remove the heat from fission. The graph here shown on the right shows also the number of plant constructions. And as you can see, there's almost over 40 plant constructions, and mainly concentrated around the continent of Asia. Now, in this slide, how does nuclear energy gets created? We use what we call the fission reaction, which it involves splitting a nuclei. Specifically, as shown kind of in this GIF, the neutron comes in and splits uranium-235 isotope into 2 fission products that carry off most of the fission energy. And this fission actually also generates other neutrons, which then we can use those neutrons to split more nuclei and have a fission, sustaining fission reaction and continuously produce nuclear energy. Now, if you look at the energy release from this reaction, in the units of electron volts is about 200 million. And when you compare it to combustion of carbon, you get only few electron volts. So this is where we get kind of our 100 million-fold in energy. The other great attribute of fission is that over 80% of this 200 million electron volt energy actually gets deposited within 50 microns or less than the thickness of your hair. And as such, we can actually take that energy more easily versus other nuclear reactions, like some of the common fusion reactions. When the reaction happens, the energy gets actually, you have to recover it a few meters away. So this is becomes a very compact, high energy source of electricity for us. Now, that's all the physics I'll talk about in this lecture. Going to the engineering, typically when you actually practically design an engineering system, these physical gains become much less, particularly if you put it in the units of a million joules or energy per unit mass. You get roughly factor of 70,000 times of higher energy density for fission that happens in our water-cooled reactors compared to other sources like natural gas. Factor of 70,000 is still quite a bit, it's still a very, very large number. In fact, if I put this graph in a linear scale, you can see that if I put things in a linear scale, you don't even see other sources of energy. And fission really is a dominant technology in terms of energy density. So then this brings us to the question that the physics really implies fission should dominate from a practical, engineering point of view. Then if you look at a natural gas plant and compare it to a nuclear power plant, as I've shown, these are two recent constructions in the US, and you see that actually per the land that this technology takes per energy produced, it's not actually that much different. The structures are, more or less are on the same scale. And if you compare the cost of these two technologies, you see that this one recently, this was a power plant constructed by Duke Energy. Originally, they wanted to actually construct nuclear energy. They ended up with combined natural gas plant. And you see that their cost is about on the order of $1.5 billion for 1.6 gigawatt electric, and they were constructing it at 2.5 years. Versus this nuclear construction that's ongoing in the state of Georgia is costing, it's not finished yet, but looks like the estimate's going to come up around $25 billion for a 2.2 gigawatt electric, and it's looking to be finished in 10 years or so. So something doesn't really add up here, given how much gain we have in energy with nuclear fission. So let's explore that a little bit in more detail. So going back to where we get the fission, the nuclear fuel. So what we do is we take uranium out of the ground and we fabricate these uranium dioxide pellets. This is just a real life size hand holding a bunch of pellets here. And each of these pellets do actually generate, over their 5-year lifetime in the reactor core, as much energy as 200 gallons of oil or 20,000 cubic feet of natural gas. So the density holds here, the energy density. And what we do is we take these pellets and we stack them up in this 1 centimeter diameter, 4 meter high thin rods. And we kind of arrange these rods in a square lattice, and we form this fuel assembly. And we have about 200 of these assemblies that make up a reactor core. And this whole core is in a reactor pressure vessel that's around 12 meters high and 4.3 meters in diameter. And a vessel like this generates roughly around 1,000 gigawatt electric of power. And if you want to go buy this vessel, you pay roughly $50 million for it. Each of these assemblies is roughly $500,000. So for over 5 years, with $150 million, you can generate a gigawatt of electricity, which comes out over a factor of 10 cheaper than even natural gas. So the energy density really does hold from a point of view of just practical engineering, looking at this vessel. But the vessel doesn't really tell us the whole all the structures and all the systems that go into a nuclear power plant. The vessel is actually is this relatively small structure sitting out here. And in order to actually get energy out, we typically, in the most popular technology, the pressurized water reactor, we have steam generators, and then we have the turbo machinery that transfers the heat to electricity. In case of typical water-cooled reactors, that efficiency, we can only actually transform 33% of the heat to the electricity, versus that combined cycle natural gas plant picture I showed last slide. That's roughly can do it 66%. So twice as efficient. So the nuclear energy generation has to be twice as much in order to get equivalent electric conversion. The other thing you see here is that there's a lot of other systems here, and that has to do with the nuclear hazard. And there is, nuclear reactions are special and unique in that the reactor is actually never fully shut down, because those fission products continue to generate heat, and you always have to circulate water through it. So you do end up with a lot of safety systems, and it does become a highly regulated industry. And all these engineering safety systems, you typically have a lot of redundancy. So you have four of the same safety systems, and a lot of diversity, various ways to always ensure that that radioactivity is contained within this a relatively large size containment building. So that's the additional cost that goes in there. For operation, there's also security. So there's concern that what if a small army comes in and starts dismantling these safety systems. And as such, for current plants in the United States, we have almost 100 over 100 security guards guarding this asset, and we're not allowed to really rely on local police or the U.S. military or the state or the state and military forces for securing this plant. And then the other thing that really contribute to that cost disparity, and particularly that construction time discrepancy, is that in the U.S., really outside of those two plants, we haven't really built any new plants, and that has resulted in loss of knowledge and infrastructure for the past 30 years. And that has been shown in any other technology sector. The loss of experience always results into cost overruns and longer construction. So we can also look at granted nuclear is coming out more expensive than initially believed. Should nuclear be treated differently? So if you look at different independent studies, and a lot of studies like to put determining the safety level of a technology by death per energy produced, and nuclear always ends up being the lowest. Particularly in the U.S., the commercial nuclear industry hasn't had really any track record of any deaths that directly relate to radiation exposure, whether it's from the actual reactor or its spent fuel, which is also commonly characterized as nuclear waste. And so you do get pretty good safety profile. And but when you look at what is the federal government, how is federal government rewarding it, you see that the federal government is really rewarding wind and solar and other renewable sources, and it's really treating nuclear like other fossil fuels when it comes to subsidy for energy generation. Same picture is true also on the state level. There's additional subsidies that get. But when you look at why is wind and solar getting subsidy, they're not really getting the subsidy for being safe. They're getting a subsidy for being carbon free. And nuclear is actually carbon free. And in fact, again, another independent study, International Panel on Climate Change in 2018, came out with the life cycle assessment of all energy sources. So they include things like carbon emissions from uranium mining to steel and concrete that goes to the systems. And they rank nuclear among the lowest. In fact, wind and nuclear were the lowest energy sources. And so even though it is from even the life cycle point of view, it is very low carbon, we still doesn't get the credit that it deserves compared to on other energy sources. So that's the reality today, particularly in the U.S. So the question is, how can we really truly harness that 70,000 greater energy density, and perhaps overcome some of these challenges just inherently with technology innovation? But to do that, really, we at least I believe that we should solve two of these grand challenges. And the first one revolves around cost of nuclear. So if you look at the ratio of where the cost for nuclear comes from, you see that you have for nuclear, it's a highly capital intensive technology, and most of the cost goes to capital costs. And that's why in those pictures I earlier showed with the natural gas versus nuclear, the cost discrepancy for capital was so much, because in reality, the natural gas plant, majority of cost actually goes to the fuel cost, which is the variable O&M. That's kind of broken down by the EIA data. And with nuclear, the fuel is actually a small part of it. It's actually very much aligned itself well with solar PV, where its bulk of it is capital. But it's also very important to not just look at the ratios, but look at absolute magnitude. Because if you see this picture, all nuclear enthusiasts will spend all their time trying to lower the capital cost. But in fact, if you look at it on the absolute scale, and there are various metrics you can use to compare technologies, historically, levelized cost of electricity, which is in units of dollars per energy produced, has been a metric. Nowadays, with complexities, may not be the greatest metric, but it is still a metric that's used as comparison. And you can see that not only the capital, but also in fixed O&M, nuclear is not doing great. And the variable cost is definitely doing better than fossil fuels, but of course, renewables come at practically free of cost, the fuel. So when you add them all up together, there's a roughly a factor of 2 that nuclear currently suffers. So we have to solve the cost. The second one that's really just as important is deployment timeline. And if you look at technology readiness level, really popularized by NASA, 1 being least mature and 9 being basically commercialized. For nuclear power plant to go to technology level of mid-level, it takes at the minimum 3 to 10 years. This is, fastest things that has been realized. And to get to really commercialization, at the minimum requires additional 10 to 20 years. On average, these things we're talking about 30 to 40 years. Now you think about where were we in terms of the electricity market, technologies for carbon-free energy sources 20 years ago, 30 years ago. And you can think about it, where we are now in terms of the cost of those technologies like solar and wind, in terms of the technology for storage, battery storage, it's night and day. And so if an idea that you start and takes 30 years to develop is probably not going to be able to compete, or it's going to be basically deprecated by the time it comes up. So we have to really accelerate the deployment timeline for nuclear. So that brings us to what my group does. And what we do is really try to focus on 3 different fronts to address these 2 grand challenges. One is digitalization, as well as system level integration. And another one is on high performing materials. And under these 3 categories, my group is composed of different researchers. So we have students and postdocs who do reactor physics calculations and modeling, basically study of where the neutrons go. We do a lot of lab work and simulation work on nuclear materials, because fundamentally, really, if you have better materials, you can go to higher temperatures and higher efficiencies. Thermohydraulics and safety is extremely important, because again, that goes back to heat removal efficiency, as well as allowing the reactor design to be licensable. And then the economics and licensing, which really tells us how effective are the innovations we're evaluating, or the innovations that we're trying to come up with. And typically what happens is that the most licensable design is typically uneconomical, and the most economical design is not licensable. And finding a happy medium becomes a very much a multidisciplinary effort design stage. So some highlights on the digitalization. Recently, we've done a project supported by Exelon, which is the largest nuclear fleet, utility in the US. And we're collaborating with Quest and Intelligence at MIT CSAIL to basically deploy the advanced AI technologies that others have developed to improve gameplay, to beat world's most experts in particular games, and that we apply it to actually nuclear design. So those assemblies that I show you, that we have 200 of them in a reactor core, each of these colors kind of represent one of those assemblies. And what happens is that in the nuclear reactor core, each of these assemblies have different enrichments. We put different neutron poisons on them. So it becomes a very high dimensional number. In fact, it's like close to 50 factorial. So you can Google what's 50 factorial in terms of number. So it becomes impossible to actually automate this thing to get the global solution to it. So what happens even today, after 6 years of commercial nuclear energy, still nuclear engineers do this process by hand and use expert input to really get to an optimal value. So we're trying to use AI to more efficiently do this process, to not only get better solutions, but also make the whole utilization of engineers more efficient. On the high performing materials, we're working with an additive manufacturing company, Freeform Fibers, where they have a laser printing technology to additive manufacture high temperature ceramics. And with that, we're looking at designing new fuel forms. We've done a lot of testing and design work, and with the aim to basically increase the operating temperature as well as the energy density that the nuclear can do. And one of the topics that we always, as nuclear engineers, try to address is to have more resilient materials on the radiation field. And here, what you can see in this graph is the blue and the red are the additively manufactured material, and the green is the commercial material that's used for nuclear application, and you can see that there's a much more resiliency against radiation for these type of materials. And you know, I just do like to highlight the collegiality of our department. I do work with a lot of senior faculty in our department. Particularly, you know, you can see this all this stuff, all this work requires multidisciplinary effort. Particularly Professor Bongiorno, Forget, and Baglietto. There's also a big educational component. I do support a lot of professional activities for teaching about nuclear to whether it's executives or students outside of MIT. And that's really one of the critical aspects, because we do need to grow this community in order to have a successful enterprise. Moving now to a little bit more specific example. So if you look at existing US nuclear plants, which generate over half of the carbon-free energy in the US. So sustaining them is, of course, of paramount importance. We do try to you know, lower that, again, addressing those grand challenges by lowering the cost. So we have projects in digital twinning, the AI I mentioned, as well as one that I'll highlight a little bit more in detail in this presentation on accident tolerant fuel, to really try to reduce the cost of fuel and O&M, which dominate the total cost of existing plants. Interestingly, if you look at this whole cost, so it takes about 300 million to run a gigawatt-sized reactor in the US, and 70 million of it is actually tied to regulation. It's not to say that if you remove regulation, the plant's going to be unsafe, but it just tells you that if you had some kind of a libertarian idea of running nuclear power plants, this is how much cost savings would incur. And it's important to note that, you know, really, since these power plants, existing power plants, always put money towards their decommissioning costs, a utility can really part ways with them if they're losing only $5 to $10 million per year. And if they part ways with them, what has happened typically, because these plants run 24/7, they get replaced by natural gas, and that basically means 25 million tons of CO2 annually added to the environment. And so, really, any type of research that can even change the cost by a few million can become important for existing plants. So, what are these accident tolerant fuels that can potentially also result in fuel cost savings? Well, when the Fukushima accident in Japan happened in 2011, the Department of Energy started a study that they really mandate the industry, the labs, and academia to come up with kind of what they call quote-unquote melt-proof fuels. And roughly 10 different classes of concepts were started explored in 2011. And currently, all the major nuclear vendors that provide the nuclear fuel to all the nuclear reactors in the US and worldwide have done their down selections, and they're planning to deploy these things mid 2020s or so. And the concept that they've more or less down selected, which is something that we were part of, is a codec cladding. And what that means is that if you remember those little pellets, they were all inserted into those metallic rods, and those metallic rods are made out of very 0.5 millimeter thick zirconium-based alloys. And what we've done is we looked at, you know, what happens when you add some coatings on them to improve their performance. And these coatings are extremely thin, you know, typically 15 microns in thickness, so much less than thick than human hair. But even this little thickness can make a profound effect. This is some tests we did in our lab. We took kind of a rodlet with an end cap, and we coated them, and then we exposed the uncoated and coated rodlet to 90 minutes to 1200 Celsius or 2200 Fahrenheit steam. And you can see just the uncoated rodlet completely falls apart versus the coated one. And in fact, it's so ductile that it starts bending a little bit. So there is some profound effect by a little bit of a coating. Some of the efforts that we did in the past 3 or 4 years was to really help and try to steer industry in the right direction by doing down selections and development of promising concepts. And we did this by doing a vast variety of testing. I'm not going to read all of them, but they range from mechanical to corrosion to fatigue testing. And we did all these variety of testing to really understand the underlying mechanisms of how these materials fail. Because once you know how these materials fail, then you can kind of know how these materials can be licensed or can be viable. For example, here's one of the ATF or accident tolerant fuel materials. and we exposed it at 300 C steam, and we saw it fall apart completely. And then we added just a simple treatment based on understanding of how that physics governed this failure, and we see that that material is no longer grossly failed. Similarly, for another material, we did a lot of sophisticated modeling based on understanding of the physics, and we calculated that over the 5-year lifetime, you're going to have many of fuel rods failing. And what you see here is the probability of failure, where every pixel in this picture represents one fuel rod. So the red means that the dark red means that it has 100% probability of failure. And that's completely acceptable because no rod should have 100% probability of failure over its lifetime. And so we did, again, based on understanding of the physics, we did some design solutions, and we were able to eliminate almost all the failures to acceptable level of risk. And so typically what happens is, we publish journal articles and declare victory there. But the important thing here is that where the solutions that we did, is it going to be licensable, and is it going to be economical at the end? And in both cases, if you have the capability to kind of go and look at the end application, the answer was no. And so you have to then do down selection and start over and start focusing on promising concept, which we did. And as such, that coding concept that everyone's focused on, that took a lot of our time. So some of the results for that coding is this. So we took some of our samples to a multi-million-dollar facility in France. They did some what we call some of the most severe postulated accidents for nuclear fuel, including loss of coolant accidents. And they basically took these rods to failure. And what we saw that based on our understanding, the failure of these rods were actually noticeably almost 100 degrees later than current fuel cladding. And the question then becomes, well, this is great, so we have more accident tolerance, but how can you use this? How can you use this to pay for the additional cost of the coating, and also even go further and reduce the overall fuel cost? Well, if you look at what limits the energy extraction rate from our fuel is fragmentation. One of the limits is fragmentation. So what happens is, to those pellets, as you get more and more energy out of them, and if they go through some of the most severe postulated accidents, they actually fragment like a powder. So if they become powderized and your cladding fails, these powders can completely come out, and you have a lot of radioactivity that's coming out of your cladding, which is your first barrier for fission product. And so through a lot of modeling and testing, we think that the coding can actually prevent this happening. So this is usually, let's say, an educated guess, but in our lab, we have the capability to actually confirm that. So we can actually model every single pipe and valve that you would need to make a licensing case to the regulator that indeed this works. So we have to kind of model the whole plant system, putting all those models and experiments feedback in there, and then do our uncertainty calculation. So the regulator never likes a deterministic answer. You always have to kind of give them what's the uncertainty. So we calculate what we call 95-95, which is the 95% confident that there's a 95% probability that these coated rods will not actually burst at 300 seconds, which is the maximum time needed to have safety injection injected in the reactor core after this severe accident. So again, going through this and having the capability to really show how the end application can actually value these new materials and new innovation is really key to kind of paint the full picture and steer the industry in the right direction. Now, switching topics to small modular reactors, which is a hot topic, and this is a part where my group has focused on for many years. If you look at, why are we not building those big reactors? I think I kind of already showed, the cost arguments is very much the case. So unless we have a lot of wind and solar being deployed, and so we get to a point where the overall cost of electricity goes up, we're not going to build those large reactors. So how are we going to make this nuclear commercial viable? Well, we got to be able to meet our market cost target, and what that means is that we got to have a good capital O&M and fuel cost, and we got to also minimize the risk. It's unacceptable to have a plant takes 10 years to build, and that there's going to be just so much interest that's going to get compounded on. So you got to minimize the project risk as well. And what the community has done, and what the particularly in Western nation, U.S., Canada, U.K., Europe, is that there's a lot of talk about small modular reactors or small reactors. So the idea is, if I take the large plant and just miniaturize it, I'll have definitely I'll probably have better attributes. So let's look at that. So what happens when I miniaturize the plant? Well, what happens is that my actually cost on all fronts goes up for various different reasons. The main one is economy of scale, because I'm using more materials per energy produced. However, what's nice about things is having a smaller plant or smaller project, my risk to those cost overruns can actually go down quite a bit, because now I have less construction time, less engineering, less people on site to do this. But again, to be commercially viable, I have to have lower the cost as well. And that requires really innovation. But the innovation you want to introduce cannot touch this. It cannot increase this risk again. So if you are like a new construction technology, well, that's going to increase your risk. Maybe it can lower the cost, but it's going to increase your risk. So it's got to be a balanced approach. And on this one, we've done a lot of work. So the question becomes, okay, how do you reduce costs, and what's the nuclear engineer's role in reducing costs? Well, the effective tool that, in my experience, I've seen over my career to reduce cost is to actually increase the reactor power density. So if I take the same reactor, all the structures the same, increase the power given the same volume, that's the most straightforward way I can reduce the cost. And that actually has been the topic of my master's and PhD at MIT under guidance of my late advisor, Professor Mujib Kazemi. And one of these, particularly my master's topic, was on developing a compact steam generator. A compact plate type steam generator, what it can do is that it can actually reduce the vessel size drastically for these small modular reactors, and it can actually allow you to take a lot more heat given the same volume. So it becomes really a key technology for these small reactors to overcome economy of scale relative to just conventional steam generators. And this actually has been adopted by a lot of different designs recently, taken 10 years, but a lot of communities are slowly adopting it. We have some also ongoing projects on it. And this is, again, one way to kind of reduce that capital cost while keeping the risk low. And so when you kind of include these type of technologies in a small modular reactor, and we apply all of our multidisciplinary capability to a reference small modular reactor that's particularly popular in Europe, what you see is that you can actually increase the power rating by not touching anything and meet everything, all your main safety criteria, from loss of flow accident, station blackout, which is a full station blackout, which is the Fukushima type accident, and a major loss of coolant accident. And you can see we can actually shown that numerically that we can actually increase the power by even 80% and still meet all of our targets by kind of doing that holistic optimization and introducing some of those innovations. I want to talk a little bit more about some of these parameters, particularly this grace period. So this grace period means that a reactor, you don't have to do anything. So you don't. So if a Fukushima type scenario happens, you have 13 days to get to that reactor to actually start pouring water in it to cool it. So the question really is, why do we need 13 days? In Fukushima, they were able to get to the site within a week. So why not 7 days? Because the difference between 13 days and 7 days is 80% more power that you can get from the reactor, that now you actually can reduce your reactor by 80%, reduce the cost of the reactor by 80%. The other one is this criteria, which basically tells you how much power you can remove from your fuel form. And the question is, why can't I go higher? Why can't I break this regulatory limit that tells me I gotta stay above 1.3 if I want to go even higher, go to 400 megawatt electric? In fact, some of those accident tolerant fuel, particularly the coating, we've done the testing that shows that under these type of accidents, the cladding is actually going to be harmless. There's going to be nothing. It's not going to even feel the accident, versus all these regulatory rules that we design our reactor really were applied to that older cladding. So again, this gives us another potential to increase the power and reduce that cost and go really overcome the economy of scale to actually have even a cheaper design than large reactor. But then you look at, how did we did this? We did this by really also increasing the flow rate as we were increasing the power rating. But if you look at the US small modular reactor offering that's on the market right now, they are all natural circulation. And you may ask yourself, well, why did they remove the pumps? Well, one of the main reasons they removed the pumps was that these designs, more or less the basis of natural circulation, were born in the 1990s, where there wasn't really that much to worry about nuclear costs. Natural gas was still expensive, and you could afford to have more safety robustness to make this a little bit more easily licensable design. Versus if you look at the countries that are actually building nuclear power plants in recent years, like Russia, China, France, you can see all their designs are actually have pumps in their small modular reactors. So this becomes a question of, we lose the degree of freedom to do design optimization, but we do get some, a lot of other safety benefits. Now I'll start ending the talk by kind of touching on some hot topics. Sure, a lot of the audience have heard of advanced reactors, non-water cooled reactors like molten salts. Well, my group does have several projects on this front. The way I see water cooled technology, even though it's a near-term technology, it does have limitations. It's low temperature, so its use is mainly for electricity. Its efficiency is relatively cool, like 33%. There's also some inherent difficulties with modularization and digitalization. And on that front, we're going to start in July 1st, a 3-year study on conceptualization of a horizontal high-temperature gas reactor under the Department of Energy Advanced Demonstration Reactor Program. And our students actually have a startup on this, the Boston Atomics. On the other front, I also play a lot of role as helping other technology developers to do this techno-economic assessment for them. So, for example, University of Buffalo is deploying seismic isolation that can be applied to all advanced reactors to streamline the design process. National Energy Technology Lab, they're deploying fiber optics, so we need modern instrumentation and control to really be able to compete with future technology. So we're doing, our group's doing irradiation study for them, as well as techno-economic assessment. And the Electrical Power Research Institute, that's looking at a new paradigm, looking at design to replace. So instead of building reactors for 6 years, where technology can be deprecated, maybe you want to design them for a shorter time, where we're supporting them with technical evaluation. And going beyond advanced, and then the latest buzzword in the energy area, transformational. We're also supporting NASA with their use of nuclear technology to take humans to Mars. And really, the way I see this is, if you look back in the day, NASA DARPA type inventions, which we're using right now, the internet and the video conferencing. Hopefully, this type of exploration can also lead to other technologies that can translate well to nuclear energy, like by some of these reactors that were built in 1950s. We're talking about 5,000 megawatt thermal at 3,000 Kelvin. So right now, commercial reactor technology operates at 10 times less the temperature. So we can definitely come up with better performing materials and translate them back to nuclear energy to really gain back our energy density. So I'd like to just conclude with acknowledgement. None of this work is possible without our students, postdocs, research scientists, faculties, admins, and of course, great alumni. We particularly, projects are, 1 or 2 years, 3 years long. So we always try to, leverage internal fellowships to get students to the graduation point. So our alumni definitely play a big role on that. And of course, Office of Nuclear Energy, that has been an integral part of it. And I'll just leave this slide as the last slide, and I try to answer this from my point of view. Can only investment really make fission great again? So can investment overcome that cost and deployment timeline, and can be a viable technology to compete in the United States? It already is doing great in a lot of parts of Asia. Well, 10 years ago, my answer was yes. It's only you give us money, we can deploy it. I think after accumulating some experience over the last 10 years, I can say it may not be the case in the United States, because there's a lot of cultural issues that has to be worked out. Cultural issues like we feel like we can always export things from, we've become a country of services. We can export manufacturing and get things cheaper from India and China. But when it comes to nuclear technology, we have to buy the $60 million vessel from Japan versus buying the $5 million same exact vessel from India. There's export control. There's these things that are really embedded into culture and the way the government does business. The other one is the societal value on sustainable energy. As you saw, federal government and state level, they value carbon-free, but they don't value nuclear as much. So are we really, last 10 years, we clearly hasn't been that serious about this. But the reality is that ship has sailed. Renewables are, the costs have gone down, and their deployment makes sense to a certain extent. So really the way I see the role of academia in supporting nuclear energy is really to first and foremost train the next generation of nuclear engineers to support the enterprise to make sure it doesn't go deprecated. Understand, use our academic knowledge to understand there are many physical mechanisms to come up with why things fail and come up with solutions. And then the last one that's very important, and I made a reference to, DARPA program. If you look at government funding and general, particularly nuclear industry, we're relatively risk adverse. We tend to be conservative, and academia is a place where we can actually start, always keep ahead of the vision of the government and really preserve that spirit of high risk. With that, I'll conclude, and I'll be happy to take any questions and discuss any topics. Thank you.
Great, thank you. A reminder to our alumni viewers to ask their questions using the Q&A feature in Zoom. We already have a lot of great questions piled up there. So I'm gonna apologize in advance if we don't get the chance to get to all of them. But the first one I'll take, I'm gonna combine two of them. So I'll read both questions and then I'll let you answer. So SMRs need factory level production to be economic. This means that that they will standardize a design that leads to hundreds of orders. This seems very unrealistic. What is your opinion on this? And then the related question is that some would say the best way to reduce cost is to increase technology or manufacturing learning by increasing volume and reducing the amount of site construction required, thereby reducing reliance on local trades and other factors that drive up upfront costs for large reactors. See if you have comments on either one or both those questions. I think they're related.
Yeah, great question. And I'm going to actually go to this slide and reference some of the great work one of my best students has done. That's Robbie Stewart, our gracious host. When it comes to factory production, the question is right on target. Again, going back to commercial viability, right? In order to be commercial viable, you got to reduce costs. So factory is one way to reduce costs because cost improves with learning. But then you got to come up with the cost of the factory, and you got to have at least 100, 200, even 1,000 orders in order to get a loan to build that factory. No one's going to do it without actually firm commitment. And particularly in the US, the supply chain has been burned by these waves of nuclear renaissance. So that's a great question. But even with that, you do have to if you look at current large reactors, and this is assuming, like, let's say we build a large reactor and then we build another one. As you can see, this is the overnight cost getting improved and gets improved over time. What happens in SMRs, this learning tends to be higher than large reactors. And this is not actually because it's dependent on factory. What happens is that they lose so much economy of scale from the amount of concrete and steel per energy produced that most of the learning actually happens on site rather than leveraging factory savings. So eventually, actually, because the amount of workforce you have is smaller, and you learn more on site by just doing it more and using the same workforce, repeating it, you actually may end up in a place that's more economical than large reactor eventually. But again, that still depends on, it does require multiple orders of a single SMR. What was the last question, Robbie?
No, I think you got to both questions.
Oh, great.
So our next question comes from Brian Marilla. And he says, all the eggs in one basket. Would the best policy be to focus all development and deployment into optimizing one attractive technology? And he gives the example of solar, rather than continuing to invest in multiple competing energy technologies.
Yeah, is that a question or a comment?
That's a question. Yeah.
Okay. So
essentially, would it be better, I think, to focus on one technology, or as opposed to having a diverse route of investment?
Yeah. So the issue, of course, with one technology is, as you saw what happened in California and Texas. When you in case of storms and unforeseeable future, if you have, like, let's say all solar, and then you have a long times of cloudiness, then you can you won't have a reliable grid. So you need to at least invest in multiple technologies. However, even within solar, you have solar thermal, you have PV, and then you have to, of course, couple them with storage. Otherwise, it's just not going to work to produce 24/7. And with storage, now you got like 100 different options. Within nuclear, you have 100 different options. My position is that we should aggressively do down selection. If something doesn't meet our target, first you got to come up with target. Say by 2030, I want to get this, and you got to stick to it. It's not just a fluffy promise. You got to stick to it. And then you do have to do the down selection. And within each technology category, you should come up with one or maybe at most two type of technologies. But I don't believe it's feasible to just go with just one carbon-free technology just because of unforeseen events and overall enterprise risk management.
Yeah, that's great. If possible, Professor Shirvan, could you turn your camera back on? I don't know if you're having bandwidth issues.
Yeah, sorry, I turn it off just in case bandwidth gets worse.
Gotcha. Great. No problem. So we have several questions around spent fuel and nuclear waste, and so one of them is, what about the cost and economics and carbon footprint of spent fuel?
Yeah. So I actually had put the my first backup slide was this life cycle assessment from IPCC. So they looked at that. So what's the first the current 100 reactors in the U.S. The always the lobbying, let's say, pitch is that you can put all the spent fuel from all the 100 reactors into you can fit it in the size of a football field, which you can do. You physically, practically, you won't do that because that's a lot of heat load and you got to secure everything, so it becomes larger. But that's the level of that's the level of footprint we're talking about. We're talking about something that can be easily managed from some kind of a consent-based repository. But the IPCC report did do the life cycle assessment of that, including as well as just uranium mining and everything, and the concrete that goes into nuclear. And what you can see here, here's the nuclear. You can see that nuclear on average, so this is the line here, on average ends up being the lowest. Actually, it's not on average. It's very much competitive with wind. The bounds become more than wind because the IPCC, they got the data from various sources, and various sources have different way of expressing that data. So you can see the bound may not be competitive, but the average on average is basically same as wind.
That's great. We have another good question here. Can you comment on the benefits and limits of extending the lives of the existing fleet as it is?
Yeah. So existing fleets. If you look at like what they call the velocity of money, every dollars generated by existing fleet is like factor of like 4 or 5 that contributes to the society. And then the major contribution from environment and sustainability is it it means 50% of the carbon-free electricity generated in this country comes from existing fleet. So that's a huge fraction that if they don't get extended, gets removed. And particularly, existing fleet, they've already paid off their capital costs. They're going beyond what they were levelized against. So we are talking about relatively good, 20 ranges from 16 to $40 per megawatt hour, depending on which area they are. So we're talking about reasonably priced sources that have an immense contribution to local, state, and national in terms of both monetary value as well as environmental value. And right now there is already 4 or 6 plants have already gotten the green light to go to 80 years. So originally they were meant to 40 years. Most of them have gone to 60 years, and even now several are going to 80 years. And I think we should keep doing it if we want to make any of these targets for carbon emission.
No, that makes sense. Thanks for that. So here's another one. There seems to be no effort to educate the public on the potential benefits of nuclear energy. For example, the lower carbon footprint that you were just talking about. What kind of public relations strategies would be necessary to reinvigorate the nuclear industry?
Yeah, that's a great question. In fact, we have me and another faculty professor Buongiorno, and the study is going to be led by MIT Stallone, David Brand, and others. We're going to start on a project. It's called basically the social behavior of scalable carbon-free technology. So why people why people could be opposed to this, and is there is the education gap causing this value? So we're going to actually start this study funded by a seed fund by MIT Energy Initiative. So we'll learn more about it. But and then at our department, we have several courses on this front, trying to educate professionals on this. And one of the courses specifically is geared toward educating journalists and NGOs and different support groups led by Professor Michael Golay to do that. So that's our outreach. And then the American Nuclear Society has a lot of K-12 outreach programs as well. But at the end of the day, yeah, it's not part of the mainstream, and I honestly don't know what can it take to do it. Perhaps it's an investment thing, or perhaps other issues. Yeah, I really don't have a good answer of how we can get there on the mainstream and try to educate folks on this, particularly on the carbon footprint.
Yeah, it's definitely a challenging topic and question. So going back a couple minutes about deployment timelines and the long construction timelines of these large plants. I know there's debate over the exact timeline, but here's a question that says, we have about 10 years to decarbonize the economy. Solar and wind are ready today, and batteries aren't that far behind. What role can nuclear reactors play for deployment in that kind of timeline?
Yeah, no, great question. It's always good to have reality checks. Again, I showed the picture, on the first slide. There's 40 reactors being constructed around the world. So, other countries are actively, building it. So, but when it comes to the U.S., right now, there is a small modular reactor that's been certified by U.S. NRC. A company had spent, as they mentioned their website, $1 billion to go through the licensing process, and their current timeline is to deploy this technology is late. This technology that can be roughly either a gigawatt electric or 600 megawatt, depending on how it's finalized by end of 2020. So that's one reactor. So that doesn't really, put a big dent to the 2030 timeline. Other small modular reactors, they can be 5 to 6 years away, but again, with the construction time and having the demonstration, we're gonna have maybe few before 2030. We're not gonna have massive numbers by 2030. The only way we're gonna have massive numbers is if we take already certified large plants, particularly the advanced boiling water reactor, as well as the advanced pressurized reactor by Korea, by KEPCO. So if there's a policy change where there's good bit of subsidy, we're gonna ask Koreans to come and build us 20 different reactors now. But other than that, yeah, the likelihood of taking a lot of nuclear would be small till 2030. But again, beyond 2030, that's I think the SMRs will be definitely ready by then, and other technology is going to be certified. So beyond that, definitely looks more feasible to make a dent actually in the overall energy, not just electricity, but overall carbon-free energy market.
Yeah, no, that's great. All right, I'm going to try and squeeze one last question in here. You'd referenced digital twins, and what about the operational learning from the 100 digital clones that are already out in the field, and what can we learn from them for as far as safety, reliability, and leveraging that data?
By 100 digital clones, is that you mean the staff there?
I think that's the operating fleet that's out there today.
The 100 reactors. Yeah. The INPO, as well as this is Institute of Nuclear Power Operations, as well as different utilities have knowledge transfer programs out there, trying to get there. EPRI has a big programs on language processing, trying to get trying to kind of digitize that experience. So there is some programs there. But at the same time, the fleet, if you look at the age of that experience, is getting close to retirement. So there's always concern about that knowledge transfer. So yeah, we should definitely try to do as much as we can to keep that knowledge intact for future needs.
That's great. Well, thank you so much. On behalf of the Alumni Association, thank you for tuning in to this MIT Faculty Forum online broadcast. And thank you again to Professor Shirvan for joining us today. We'll be sure to forward all the questions asked via the Q&A menu bar to our speaker today. And Alumni Office staff will keep the chat window open for discussion purposes for another 15 minutes from now. And this broadcast will be available on the MIT Alumni Association YouTube channel within a week of today's airing. And thank you again for participating today.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.